Professor Skafidas, your field of neural engineering is about as cutting edge as it gets. What are the fundamentals?
So neural engineering is about bringing together neurologists, neuroscientists, mathematicians, computer scientists, biologists and engineers to try to understand how collections of neurons work together in order to compute, form memories, and how those neurons can some way be disrupted in order to lead to pathological states. What we are doing is putting neurons together in order to create a brain in a dish, and that has enormous applications. Most importantly, it allows us to create a disease model for that particular disease that we're trying to investigate, interrogate, try to understand what the fundamental causes or pathology of that disorder is.
So what's the holy grail here? I mean, one part of it is clearly to find more efficacious drug treatments, but is there something else that's really out there on the horizon?
In the short term, it would be a model for a patient where we can actually better target appropriate treatments for that patient. In the medium term, it is trying to understand what are the fundamental causes of some of these diseases and disorders. So it's 2015 and we still don't know what the causes of schizophrenia are. We know how to treat some of the positive symptoms like the hearing of voices and things like that, but a lot of the other things we don't know how to treat. This type of modelling will really try to get to the fundamental questions on what is really happening there. For example, if patients have suffered a stroke or have some other deficit, we can actually, transplant that tissue, but that's way into the future. We're talking about 30, 40 years.
You're talking about, I suppose, a printable brain, right? And surely the prospect of other printable organs?
People are in the process of printing livers using the same technology that we're using to print brains. What's interesting is with these brain in a dish type technologies, what we're able to do is we're actually able to train them. So you're actually able to get them to respond to their environment. But it's not like learning where you read to them and they can read the text back to you or understand what the text means. Here, what we do is we print these collection of cells in the right environment over an electrode array, which you can think of them as little wires where we can actually electrically stimulate and record from these collection of wires, high density wires. And what we're able to do is we can actually put in appropriate signals, and the collection of neurons responds in a particular way to that to that stimuli. Now, we've joked around about asking some of the people in the faculty to donate some of their skin cells so we can actually make comparisons between some of the academics. We haven't had anyone offer us any of their skin cells in order to be able to generate a model of their brain in a dish and see, can we train one better than the other? So I think within the next 5 to 10 years, this type of technology will revolutionize drug discovery, our understanding of disorders, better treatments, and also potentially allow us to come up with treatments faster and more cheaply.